Section 4.9, Rank, Nullity, and the Fundamental Matrix Spaces. Let's start by proving that the row space and the column space of a matrix A have the same dimension. Remember that elementary row operations do not change the dimension of the row space or of the column space of a matrix. Thus, if R is any row echelon form of A, it must be true that the dimension of the row space of A is equal to the dimension of the row space of R, and that the dimension of the column space of A is equal to the dimension of the column space of R. So it suffices to show that the row and column spaces of R have the same dimension, then everything's equal. But the dimension of the row space of R is the number of non-zero rows, and the dimension of the column space of R is the number of leading ones. Since these two numbers are the same, the row and column space have the same dimension. So this common dimension of the row space and column space of a matrix is called the rank of A, and is denoted by rank A. The dimension of the null space of A is called the nullity of A, and is denoted by nullity of A. As an example, how about we find the rank and nullity of the matrix A given over here? So what we'll do is we'll first put it in reduced to our echelon form and then just count up the leading ones. So how about we multiply the top row by -1 to get a leading one over there, and then we'll add 3 times it to this row, and 2 times it to this row, and 4 times it to this row, so that we can get zeros underneath. So we'll start by writing 1, -2, 0, -4, -5, 3, and then we'll get zeros underneath by doing 0, -2, 2, 12, 16, -5, and then the third row also becomes 0, -1, 2, 12, 16, -5, and so does the fourth one. So that's pretty convenient. That means that we can just take multiples of the second row and add it to the third and fourth rows in order to cancel them out and get zeros. So the last 2 rows will be 0. I'll also multiply that row, the second one, by -1 to get a leading 1 over there, and subtract 2 of it from the first row in order to get a 0 on top of the leading 1. So I'll end up with 1, 0, -4, -28, -37, 13, 0, 1, -2, -12, -16, 5, and zeros underneath. So now I can just count up. I can see that I have 2 leading ones. So that means that the dimension of the row space, well, the dimension of the column space is equal to the dimension of the row space, which is 2. So that means that the rank of A is equal to 2. Next, to find the nullity, we need to solve the equation AX equals 0. So we should write A with an extra column of zeros. So we'll write 1, 0, -4, -28, -37, 13, 0, and 0, 1, -2, -12, -16, 5, 0, and then the other ones were 0. I'm just writing the reduced row echelon form instead of writing A, because that basically is what we would have to do anyway in order to solve this equation. I just added this extra column of zeros. Okay, so reading off, we see that x1, this first variable, 1 times it, minus, well, there's 0x2s, how about 4x3s, minus 28x4, minus 37x5, plus 13x6 is equal to 0. And we also have that x2, because there's no x1 over there for the second row, x2 minus 2x3 minus 12x4 minus 16x5 plus 5x6 equals 0. Okay, so that means that we can solve for x1 and see that x1 is equal to 4x3 plus 28x4 plus 37x5 minus 13x6, and x2 is equal to 2x3 plus 12x4 plus 16x5 minus 5x6. Okay, so how about I parameterize these solutions? I'll replace x3 with r, x4 with s, etc. So I'll get that x1 is equal to 4r plus 28s plus 37t minus 13u, just by relabeling. I'll get that x2 is 2r plus 12s plus 16t minus 5u. x3 is just r, x4 is s, x5 is t, and x6 is u, my free variables. So that means that I have, in vector notation, x1, x2, x3, x4, x5, x6, it's my vector x, is equal to r times 4, 2, 1, 0, 0, 0, plus s times 28, 12, 0, 1, 0, 0, plus t times 37, 16, 0, 0, 1, 0, plus u times minus 13 minus 5, 0, 0, 0, 1. Okay, notice these four vectors form a basis for the null space, because they form a basis for the solution set of x's that make the equation true, equaling 0. So that means that the nullity of A is the dimension of that space, number of vectors in the basis, so that's 4. Next up, what is the maximum possible rank of an m by n matrix A that is not square? Well, let's see. If it's m by n, then that means that the dimension of the row space of A must be less than or equal to n. Remember that there's n columns, and the number of columns is the maximum number of vectors you could have in a basis for the row space of A, so the dimension must be less than or equal to n. Similarly, the dimension of the column space of A is limited by the number of leading ones, which is limited by the number of rows, so it's less than or equal to m. So that means that the rank of A would have to be the smaller of these two, because these two guys have to be equal to each other, so it must be less than or equal to the minimum between m and n. Next up, we have the dimension theorem for matrices. If A is a matrix with n columns, then the rank of A plus the nullity of A must be equal to n. Let's prove this. Since A has n columns, then the homogeneous linear system AX equals 0 has n unknowns. So that means that these fall into two distinct categories, the leading variables and the free variables. So we have the number of leading variables plus the number of free variables must be equal to n, the n unknowns. but the number of leading variables is the same as the number of leading ones in any row echelon form of A, which is the same as the dimension of the row space of A, which is the same as the rank of A. Also, the number of free variables in the general solution of Ax equals 0 is the same as the number of parameters in that solution, which is the same as the dimension of the solution space, which is the same as the nullity of A. It's kind of like over here, we had these 4 parameters, and we had 2 leading ones. So this gave us the rank, this gave us the nullity. Together, the rank plus the nullity is equal to the number of columns. Over there it was 4 plus 2 equals 6, or 2 plus 4 equals 6, depending on which one you want to say rank nullity first, but either way. How about we verify this for the matrix in example 1? Well, I just gave you a verbal explanation, but I'll write it down. We'll write A equals -1, 2, 0, 4, 5, -3, 3, -7, 2, 0, 1, 4, 2, -5, 2, 4, 6, 1, and 4, -9, 2, -4, -4, 7. And as we saw before, the rank of A was equal to 2, so if we add it to the nullity of A, we get 6. In other words, by example 1, rank of A is equal to 2, and nullity of A, well, I used like a lowercase n, so I'll try to be consistent. Nullity of A is equal to 4, so this equation is true, or at least it's verified in terms of the theorem. If A is an n by n matrix, then the rank of A is equal to the number of leading variables in the general solution, and the nullity of A is equal to the number of parameters. We basically saw that that was true, but now we're officially stating that it is true in every case. Without proof, but you can see why it's true. As an example, how about we find the number of parameters in the general solution of Ax equals 0 if A is a 5 by 7 matrix of rank 3. Okay, well, the nullity of A would have to be equal to n minus the rank of A, but in that case, number of columns is 7, so the rank of A, which is 3, would give us 4 for the nullity, which is equal to the number of parameters. Next, let's find the rank of a 5 by 7 matrix A for which Ax equals 0 has a 2-dimensional solution space. Well, the rank of A is equal to n minus the nullity of A, and again, number of columns is 7 minus the nullity, they said is 2 because it's 2-dimensional solution space, so the rank is 5. If Ax equals b is a consistent linear system of m equations in n unknowns, and if A has rank r, then the general solution of the system contains n minus r parameters. We won't prove that, but it's true. The following spaces associated with matrix A and its transpose, A transpose, are called the fundamental spaces of matrix A. So we have the row space of A, we have the column space of A, we have the null space of A, and the null space of A transpose. The row space and null space of A are subspaces of Rn, whereas the column space of A and the null space of A transpose are subspaces of Rm. The null space of A transpose is also called the left null space of A because transposing both sides of the equation A transpose X produces the equation X transpose A equals 0 transpose, in which the unknown is on the left. The dimension of the left null space of A is called the left nullity of A. Let's focus on a transpose for a little bit. If A is in a matrix, then the rank of A is equal to the rank of A transpose, it turns out. Let's prove that. Well, the rank of A is equal to the dimension of the row space of A, which is equal to the dimension of the column space of A transpose, so that has to be equal to the rank of A transpose. Pretty easy proof, but notice that implies that if the rank of A is equal to R, then we have that the dimension of the row space of A is equal to R, the dimension of the null space of A is equal to n minus R, and so the dimension of the column space of A is equal to R, and the dimension of the null space of A transpose is equal to m minus R. Notice that even though A and A transpose have the same rank, they both are, they have different null space dimensions, different nullities, because you subtract the rank, but you still have to start with the number of columns, and the number of columns and rows switch when you transpose a matrix. So notice also we didn't put the transpose for most of these because we only mentioned it for the null space, because the column space of A is equal to the row space of A transpose, right? That's already the same, and the row space of A is the column space of A transpose. So I'm gonna put a little equal. So most of these are the same. The distinct ones are basically these four. How about we find bases for the fundamental spaces of the matrix given over here? So what we'll do is we'll reduce this matrix A. So I'll write -1, 2, 0, 4, 5, -3, and I'll adjoin it with the identity matrix 1, 0, 0, 0, so that way I can keep track of what happens to the identity matrix. 3, -7, 2, 0, 1, 4, 0, 1, 0, 0, 2, -5, 2, 4, 6, 1, 0, 0, 0, oh, I needed a 1 over here, and then 4, -9, 2, -4, -4, 7, 0, 0, 0, 1. Okay, so here's matrix A, and here's the identity. Let's reduce that. So, as before, because notice this is the matrix we've already looked at, where these guys end up being the same after we subtract off that first row. So we'll get 1, -2, 0, -4, -5, 3, and then the top row of the identity becomes -1, 0, 0, 0. We just multiplied by -1, and then the second row became 0, -1, 2, 12, 16, -5, but then we had to add 3 of the first one, so we get a 3 over there, 1, 0, 0, and for the third row, it became 0, -1, 2, 12, 16, -5, and then we added 2, so it was 2, 0, 1, 0 for our modification to the identity matrix. And last we have 0, minus 1, 2, 12, 16, minus 5, and we'll add 4 of the top row. Okay, cool. So this, just to separate it still. Okay, so let's keep going. So we'll get 1, 0, minus 4, minus 28, minus 37, 13, as we did before. And then the top row of the identity. Remember, we had to add 2 of these guys to that. So, or negative 2, because it has to be negative in order to cancel. So this will become a minus 7. And then minus 2, 0, 0. And then we have 0, 1, minus 2, minus 12, minus 16, 5, minus 3, minus 1, 0, 0, by multiplying the second row by minus 1. And then to cancel out these rows, we have to add this new row to the bottom 2. So we'll get 0, 0, 0, 0, 0, 1 more 0, and then minus 1, minus 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, minus 1, 0, 1. Okay, let's keep going. And we'll get 1, 0, minus 4, minus 28, minus 37, 13, 0, 1, minus 2, minus 12, minus 16, 5, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Notice that this was already in reduced to echelon form, but this part makes it so that we still have a little bit more work to do, because now we have to get a leading 1 over there. So we also have to get zeros above it. So we'll end up with 0, 5, minus 7, 0, 0, 2, minus 3, 0, just by multiplying this by minus 1 and adding 7 to that one and 3 to that one. So we'll get 1, 1, minus 1, 0, and let's get a 0 underneath. So we'll get 0, 1, minus a half, and minus a half. Okay, almost done, because we have this leading 1, we have this leading 1, we just have to get zeros over there. Okay, so let's do that. We'll get 1, 0, minus 4, minus 28, minus 37, 13, 0, 1, minus 2, minus 12, minus 16, 5, and then the 2 0 rows. And then the part that I'm concentrating on, 0, 0, minus 9 over 2, 5 over 2, 0, 0, minus 2, 1, 1, 0, minus a half, half, 0, 1, minus a half, minus a half. Okay, excellent. So now I have, let's call this matrix R for the reduced to echelon form. We'll call this matrix E. So now I have the basis of the row space. So I'll call it the row space basis. Okay, and that'll just be this top row over here. So I'll write that in column form. So that's 1, 0, minus 4, minus 28, minus 37, 13. Okay, and the other vector is the second row. So that's 0, 1, minus 2, minus 12, minus 16, 5. So that was the easy part, was getting the basis for the row space. For the column space basis, running out of space a little bit, but that's okay. We have, oh, let's see, we have these two leading ones, so those correspond to the columns in A that make up our column space basis. So that's the first two columns. So that's minus 1, 3, 2, 4. And it was 2, minus 7, minus 5, 9. Okay, great. Oops. Okay, so now let's get the left null space, if we can fit it. We're sure we could squeeze it in. Left null space basis. So just reading off of the leading ones that we ended up with in our new matrix E over here that we got modifying the identity, we get 1, 0, minus a half, half. So 1, 0, minus a half, half. And then the other one is 0, 1, minus a half, minus a half. If you're a little confused as to why that constitutes the basis for the null space of A transpose, well, I don't blame you, but notice what we've basically done is we've taken A and we've found essentially over here an inverse for A. It won't always be an inverse for A because A doesn't necessarily have to be invertible, but we modified this so that we can get something so that if we were to take E times A, it should equal R, right? So remember that the null space of A transpose is the thing that we get from A transpose x equals 0. It's all the solutions that make that true, which is the same thing as saying x transpose A equals 0 transpose. So we're looking really for when E is equal to the zero rows in R. Here's the part where E, where it equals the 0 part in R. So these rows right over here are exactly what we get, or exactly what we need in order to make this equation true, which is what we need to make this equation true. So that's why these guys constitute the basis for the null space of A transpose, aka the left null space basis. It'll always end up being the rows that you get with the leading ones in the matrix that you get over here when you take A adjoined with the identity and you reduce it to some matrices Re. Remember that the dimension of the null space of A transpose is M minus R. So we had M equal to 4 in this case. This is a 4 by 6 matrix. So it's 4 minus r, but the rank dimension of the row space was 2. So 4 minus 2, it has to be the last 2 rows. There had to just be 2 vectors in here. Next up, if W is a subspace of Rn, then the set of all vectors in Rn that are orthogonal to every vector in W is called the orthogonal complement of W and is denoted by the symbol W perp for perpendicular. Perpendicular is often used as another word for orthogonal in practice. If W is a subspace of Rn, then W perp is a subspace of Rn. The only vector common to W and W perp is the 0 vector, and the orthogonal complement of W perp is W. As an example, what is the orthogonal complement of a line W through the origin in R2? What is the orthogonal complement of a plane W through the origin in R3? Okay, so how about we draw this to figure it out? So here's my x-axis, here's my y-axis. I need a line W, so here's a line W, and here will be W perp, just the line perpendicular. Oops. Like that. Okay, and as for orthogonal complement of a plane, well, I need some 3 dimensions now, so let's see. How about I start drawing my plane? And then I can finish drawing my lines around it. I'll make this a little bit behind. Okay, so that'll be my z-axis, this will be my y-axis, and I'll make this my x-axis. Okay, so then I need something that's always orthogonal. So you might be tempted to draw another plane that cuts through here and just say, okay, it's the plane perpendicular, but it's actually not, because if you were to do that, you would have an entire section over here where they have vectors in common. This would be a vector in both then. So that can't be. They have to have only the 0 vector in common. So in order to make sure that the only vectors we're looking at are perpendicular ones, the orthogonal complement is actually also a line. It is the line that goes to the origin. It's going to be perpendicular. Let's see if I can draw that. Looks a little bit like that. This is what W perp would look like. If A is an m by n matrix, then the null space of A and the row space of A are orthogonal complements in Rn, and the null space of A transpose and the column space of A are orthogonal complements in Rm. I'm not going to prove it, but it's true. This lets us add to our equivalent statements that we've steadily been accumulating. We now have that A having rank n is equivalent to A having nullity of 0, because it would have to add up to n, or the number of columns for A, number of rows for A transpose. The orthogonal complement of the null space of A is Rn, and the orthogonal complement of the row space of A is 0. These are all equivalent to the statements that we had before. A linear system with more constraints than unknowns is called an overdetermined system. A linear system with fewer constraints than unknowns is called an underdetermined system. Let's let A be an m by n matrix. We have 2 cases, an overdetermined case and an underdetermined case. In the overdetermined case, if m is greater than n, then the linear system Ax equals b is inconsistent for at least one vector b in Rn. In the underdetermined case, if m is less than n, then for each vector b in Rm, the linear system Ax equals b is either inconsistent or has infinitely many solutions. Let's prove this. For A, let's assume that m is greater than n, in which case the column vectors of A cannot span Rm. Okay, so then there is at least one vector b in Rm that is not in the column space of A, and for any such b, the system Ax equals b is inconsistent. For part B, let's assume that m is less than n. For each vector b in Rn, there are two possibilities. Either the system Ax equals b is consistent or it is inconsistent. If it is inconsistent, then we're done. If it is consistent, we have to show it has infinitely many solutions. But we know that the general solution has n minus r parameters, where r is the rank. And we know from example 2 that the rank of A is at most the smaller of m and n. So that means that n minus r is greater than or equal to n minus n, which is greater than or equal to 0. So that means that the general solution has at least one parameter, and hence there are infinitely many solutions. As an example, what can we say about the solutions of an overdetermined system Ax equals b of 7 equations in 5 unknowns in which A has rank r equals 4? Well, notice the number of unknowns is bigger than the rank, so we can tell that there's going to be number of parameters in the solution is going to be greater than 0. So the system is consistent for some vector b that lies in R7 such that the number of parameters in the general solution, meaning for any such b, it's got to be at least one b that works, and the general solution is, well, remember it's n minus r. In this case, n is 5. It's our 5 unknowns, 5 columns, and the rank is 4, so it must be one parameter in the general solution. What can we say about the solutions of an underdetermined system, Ax equals b, of 5 equations in 7 unknowns in which A has rank r equals 4? Well, it's underdetermined, so that means that it could be consistent or it could be inconsistent. So we'll write the system may be consistent or inconsistent, and if the system is consistent, then the general solution has n minus r parameters, right? That's 7 minus 4, because there's 7 unknowns, so that's 3 parameters. Okay, how about we finish with an example? Under what conditions is the linear system given over here consistent? How about I write out the coefficient matrix for this guy? So that'll be 1, 1, 1, 1, 1, minus 2, minus 1, 1, 2, 3, B1, B2, B3, B4, B5. Okay, so let's start reducing that. Okay, so let's get zeros over here. So by subtracting off, I'll get 1 minus 2 B1, I'll get 0, 1, B2 minus B1, I'll get 0, 3, B3 minus B1, I'll get 0, 4, B4 minus B1, and I'll get 0, 5, B5 minus B1. Okay, let's keep going. I would like to get a leading one over there. I already have it. So let's get zeros above and below. So my top row will become 1, 0, B1 plus 2, B2 minus B1, because I have to add 2 of this row over here to cancel it out. And I'll keep the 0, 1, B2 minus B1 row, because that row is already good. Then I have to get a 0 underneath, so I'll get 0, 0. I'll take B3 minus B1 that was already there, and I'll subtract off 3 of the row above, so 3 of B2 minus B1, and then I'll get 0, 0, B4 minus B1, I already had it, minus, there's a 4 over here, so I have to take 4 times this, so 4 times B2 minus B1, and then my last row, 0, 0, B5 minus B1 minus 5 times B2 minus B1. Okay. So that is reduced, but maybe I can clean it up a little bit. I'll simplify some of this stuff over here, because notice I've got 2B2, I have minus B1, minus 2B1 plus B1, so I could just get B1, so I could rewrite the top row as 1, 0, 2B2 minus B1, second row is still good, simplified, so B2 minus B1, then third row I'll simplify and I'll just write B3 minus 3B2 plus 2B1, combine like terms, and fourth row B4 minus 4B2 plus 3B1, and then my fifth row B5 minus 5B2 plus 4B1. Okay, nice. So this means that I have 2B1 minus 3B2 plus B3 equals 0. How about I leave a little space? I'll get 3B1 minus 4B2 plus B4 equals 0. And I'll get 4B1 minus 5B2 plus B5 equals 0. I just pulled off the rows that were equal to 0. Okay, so how about we write this in turn as a matrix? So I'll write 2 minus 3, 1, 0, 0, 0, 3 minus 4, 0, 1, 0, 0, 4 minus 5, 0, 0, 1, 0, because basically what I'm trying to do is I'm trying to find values for all these b's that will actually work and, you know, make this equal to 0. So it makes sense that if I want to solve for those b's, that I would just solve for this thing equaling 0 over here. Okay, so I will reduce this new matrix now. I'll get a 1 on the top by dividing by 2, and then I'll get zeros underneath by subtracting. So I'll get 1 minus 3 over 2, half, and then 0, 0, 0, and I'll get 0 underneath, minus 3 over 2, 1, 0, 0. And I get, last but not least, 0, 1, minus 2, 0, 1, 0. Okay, good. I would like now to get a leading 1 over here, and 0s above and below. Okay, so let's continue to manipulate this. Okay, I'll end up with a top row of 1, 0, minus 4, 3, 0, 0. I'll get, how about I just multiply this row by 2 and then subtract off from these guys to cancel it out. Okay, so I'll get 0, 1, minus 3, 2, 0, 0, 0, 0, 1, minus 2, 1, 0. Yep. Then 2 times this, cancel the okay, good. So then I have 1, 0, 0, minus 5, 4, 0, because I want to get these guys 0. I'll get 0, 1, 0, minus 4, 3, 0, and we are done. Okay, so now we can just read off the solution for the b's. So we have b1, then no b2, no b3, so I'll skip a little space, and I'll get minus 5b4 plus 4b5. That has to equal 0, and I'll get that b2 minus 4b4 plus 3b5 has to be 0, and b3 minus 2b4 plus b5 has to be 0. Okay, so that means that b4 and b5 are my free variables. I'll just make them parameters, let's say r and s. This means in order for our b's to give a valid solution, b1 would have to be 5r minus 4s, b2 would have to be 4r minus 3s, b3 would have to equal 2r minus s, and b4 would just be r, it could be anything, and then b5 would be s.